Hey scholars, it's good to be back with you. Now we've learned how to solve systems of linear equations using row operations. It's time to dig in a little farther with the details of matrix algebra. Now as we go on, it may seem like half of what we're doing here is learning terminology, and there's something to that. So what I want to do is let's get some lingo out of the way first, and then we'll go into the mechanics of how to multiply matrices and vectors together. So first thing we need to know is how do you write a matrix down in general? Well, what you'll see in the books is this. And this is very standard notation. And so what you'll see is any variable name or element name, we'll call this A. We'll call this matrix lowercase a. So A11 is the first row, first column. A12, first row, second column. Second row, first column, second row, second column. So these subscripts here are just the address in the matrix, the row number and the column number. So that's pretty straightforward. So let's get some names out of the way here. First thing you'll hear about probably is a square matrix. A square matrix is one that has the same number of rows and columns. All right, so let's say M equals the number of rows. Whoops, there we go. And N is the number of columns. You'll see this terminology used quite a bit. And square just means N equals M. Capital N equals capital M. Right. Now, not all matrices are square. You have rectangular matrices appear all the time. But square matrices have some properties that we particularly like. And the most important one is that you can invert a square matrix. You can essentially divide by a square matrix. We don't call it division, we call it inversion. We'll go over that here probably in the next section here. So another one is a symmetric matrix. Well, what's a symmetric matrix? Well, first thing you need to know is there's this thing called a diagonal. I've mentioned it before. So that's the diagonal. And let's make these two numbers, we'll call this n little m and little n. So those are indices that'll change. Big M, big N are the total number of rows and columns. So diagonal little n equals little m. So A11, A22, A33, A44, on down. So this is called the upper triangle, and that down there is called the lower triangle. Well, right here there's only one element there, but you can see that if there are more elements, there's a triangle, and there's a triangle, and those will be also full of matrix elements. So upper triangle, lower triangle, and there's this thing called a symmetric matrix. There we go, that's better. All right, it means that when you reverse the indices, the elements are the same. Okay, so A12 equals A21 in a symmetric matrix. Well, why do we care if it's symmetric or not? Well, when you're calculating on a computer, matrices that are symmetric are easier to work with than matrices that aren't. And it gets even better. In some problem formulations, the matrices have to be symmetric. So in structural problems, things called mass matrices and stiffness matrices are symmetric. You can even use that as a check in your calculations. If you're writing code and you check the resulting matrices, if they aren't symmetric, if they are not symmetric, something's wrong. You've made a mistake in your code or made a mistake somewhere else. So symmetric matrices are important. Okay, that's probably enough terminology for now. Let's get into the mechanics of how you multiply a matrix times a vector and then a matrix times a matrix. So let me clean off my board here. Okay, this is probably the simplest matrix multiplication problem there is. A 2 by 2 matrix multiplied by a 2 row, 1 column vector. Vector is just as a column or a row. This one's a column. When you multiply a matrix times a vector, what you're doing is you're multiplying the elements along a row and a column and then summing them up. So for this problem, I'm going to multiply A1 times B1 plus A2 times B2, and that will go right here. So let me write this out, and you'll see the pattern here. There. So A11 times B1 plus A12 times B2. If I had more columns and more rows here, the pattern would just keep going. So for this one, I'm multiplying the first row of the matrix by the first column of the vector to get the first column of the product. It works the same way here. So I'll say A21 times B1 all right, so A21 B1 plus A22 B2. So this is pretty easy to read. The first index tells you the row, so that's row 1. First index there tells you the row, that's row 2. Now you can't multiply just any matrix by just any vector. They have to be compatible. The dimensions have to be compatible. So what that means is the number of columns of the matrix has to equal the number of rows of the vector. So before we said the total number of columns was capital N, so capital N of A has to equal capital M of B. Right? And that's true. Matrices are compatible. The matrix and the vector are compatible. They can be multiplied. So what happens when we try to multiply two matrices together? Well, it's kind of an extension of this. It follows the same kind of pattern. Okay, I cleaned off my board here and I rewrote the problem where A is a matrix and B is a matrix. Now we have the same compatibility requirement. So the number of columns of A must equal the number of rows of B. These do not have to be square matrices. They can be rectangular, but number of columns of A has to equal the number of rows of B. So what's this going to look like? Well, it's exactly the same as we did before, but with kind of an extension. So I'm going to go across the row here, down the first column there. So it'll be A11 times B11 plus A12 times B21. Where does it go? Well, first row, first column will go in the first row, first column over here. I'm going to write this out. All right, first row, first column. This will be the first row, first column of this matrix. Oops, that's not going to work. I'm going to leave that. I'll write that in later. So the size of the matrix you get out the other end is not necessarily the size of either one of those. So let's do a couple more here. I'll go ahead and write all these out for you. And I'll speed up the video so you don't have to spend a lot of time watching. So let's just go through the pattern here real quick to make sure you're on board. You can skip this if you need to. Okay, so first row here, first column there. First row, first column. Okay, A11 times B11 plus A12 B21. So there's the first row, first column. Let's go over here now. See if I can do this without getting my head in your way. So A11 B12 plus A12 B22, that's over there. Now let's go to the second row, first column. Second row, first column. So that must be A12 B11, A12 B21. There it is. And finally, second row, second column, which is right there. Now, I've worked this out in detail here for a 2x2 matrix, but you can see that it doesn't really matter how many elements are in these matrices. So this is easy, although tedious as the matrices get bigger. It's dirt simple in MATLAB. So let's go try that.